Hello everyone, I'm Vinay Kumar Singh, research scholar care of Dr. Raghvendra Singh in the Department of Botany, Banaras Hind University, and I'm going to present a PPT on constructing a phylogram using BEAST. So, as you know, Bayesian inference analysis is one of the most popular analysis in the recent years for making phylogenetic tree, and other methods you have already know or you are knowing about that is neighbor joining and maximum likelihood, maximum parsimony, etc. There are different methods using which we can construct a phylogram. It is up to you, either you choose distance based methods or character based methods. So first thing, why is phylogenetic important? You already know about the lineage classification system, where lineage classification was actually based on the sexual system. They only consider the stamen, their number, fusion, etc. And it was an artificial classification system using which we cannot compile or group of plant, or we cannot group a plant based on their overall similarity. Second, the classification system was Bentham and Hooker classification system, where more of the similarity was considered and the plants were placed based on the overall similarity. In recent years, angiosperm phylogenetic classification system was developed, whereas the some conservative genes like RBCL, MAT-K, and ITS were used to construct the phylogenetic tree, wherein we can see that the evolutionary relationship between the plants. If I take an example of Fabaceae, then you already know that the Fabaceae family is traditionally classified into three subfamilies, which is Caesalpinioideae, Mimosoideae, and Fabioideae. Fabioideae is also known as Papilionoideae. These are the subfamilies. Sometimes they are also treated as families in some classification. And according to the Bentham and Hooker, there is the key for identifying the members of these subfamilies. Like in the subfamily Mimosoideae, you will find that the flowers are actinomorphic, and in Caesalpinioideae and Papilionoideae, the flowers are zygomorphic. To identify the Caesalpinioideae from Papilionoideae, you have these characters like corolla estivation in Caesalpinioideae is ascending imbricate, and the posterior petal is innermost. There are 5 petals and they are polypetalous. Stamens are either polyandrous or monoandrous, and in Papilionoideae you will find a descending imbricate estivation, and here posterior petal is outermost. So what happened in the recent years that these conserved genes here is the classification presented by the Legume Phylogenetic Working Group LPWG in 2016, wherein they uses the Maturay's K sequences from 3,696 species, 3,696 sequences representing about 19,500 species. As I have told you that in the recent years these conserved genes were used to check the evolutionary history, and after this analysis they have found that the traditional there were 3 subfamilies according to morphological classification, and by using these conserved genes they have found that there are actually 6 subfamilies can be categorized into Fabaceae family. And the most important thing is Mimosoideae is now considered as under the subfamily Caesalpinioideae. So it is one of the major clade in the Caesalpinioideae subfamily. So now you have a different key to identify the members of these 6 subfamilies. So it is by using these conserved gene, the family is now considered as they have multiple clades which are now monophyletic, And in recent years, as I have said, that many of the genera and many of the species can be placed into their respective genera correctly. They have been correctly identified, and the evolutionary relationship was inferred very precisely by using these. So the very first thing is when to use this B software. As I have said that we use this software to construct the phylogram using the Bayesian interference. So it is one of the software to construct Bayes program. Others are Mr. Bayes, Bayes 2, Philo Bayes, Batwing, etc. These software can also be used to construct the phylogram for Bayesian interference. So the first thing is we should take tissue from any organism like plant or fungi. Then we do DNA isolation of that. Then PCR amplification of targeted genes using a specific primers will be done, and DNA sequencing of those amplified region will be done. And for alignment, there are many softwares like Mega. You can do alignment in Mega itself, or there are websites also like RxML, where you can use the web servers to align these sequences using one of the methods like ClustalW or Muscle. And after that, after these alignment, we using these alignment, we construct the phylogenetic tree. There are many methods for constructing phylogenetic tree like neighbor joining, ML and BI, and we use these B software in Bayesian interference, from which you will get a phylogram. So how to use Beast? The first thing is to ensure that your PC or laptop has Java installed. So you will have to download and install Java. Second, you will have to download the latest version of Beast. And for your knowledge, when you will be downloading the B software, it will contain 5 applications within it, like Beast, Beauty, Lock Combiner, Tree Annotator and Tree State. In addition, you will need other applications like Fig Tree, C View, Tracer and Beagle application. Here is the outline of run. Firstly, you will have to use the C View application, because Beauty, the first software you will use is Beauty. For Beauty, Beauty cannot read the aligned FASTA files, so you will need to Nexus format alignment, and for that you will need a CView application. So using CView application, you will have to convert your FASTA sequences to the Nexus format, so that the Beauty can read that file. And one note is for you that we cannot use the Nexus file format from the Mega software. So don't use the Nexus file from the Mega. Beauty is not going to read that. So use CView to convert your aligned FASTA to convert into Nexus, so that we can run the Beauty application. The second application is Beauty. Beauty is a graphical user interference application for generating Beast XML files. So Beauty is a software which is meant for generating XML files. So what is the function of Beauty? Beauty set up the conditions for the run. Like here you will see the partitions, models, etc., priors, etc. you will find in the Beauty. So we set all the conditions so that we can generate a file, XML file, which will be used in the B software. Here you will need another software which is Beagle. Beast needs Beagle library to run. So ensure that your laptop or PC also have downloaded and installed Beagle. So after that you will have to run Beast. Open your Beast application and open your file, XML file which was generated from the Beauty. Run Bayesian analysis using the XML file generated from the beauty, and beast is going to write generate .tree files which contain thousands of trees. Okay, so after running beast you will need a tracer application. So go and open your tracer application. What is the function of tracer? It summarizes those trees, thousands of trees, and help you to choose how many early low probabilities trees to discard from the final consensus tree. So the function of tracer is to burning the initial low probabilities tree. So when you open a tree, you can see how many of the percentage or how many million of the trees of low probability trees were discarded. Okay, so this tracer is going to use the .log file which is generated along with the tree file in the beast. So the another software you will need is tree annotator. Tree annotator is going to use the file .tree which is generated from the beast. And what is the function of tree annotator? It makes the consensus tree. As you know, the tree file contains thousands of tree. So tree annotator is going to make a consensus tree based on these thousands of tree, and it will also add the posterior probability, which is like your bootstrap analysis. It is the statistics of a reliability for each node. And in the last you will need fig tree. Fig tree is a tree drawing program compatible with beast and tree annotator. There are two other applications along with these file. When you will download beast, you will also get the log combiner and tree stat. I don't know the function of these applications, and these are not actually used while making the phylogenetic tree. So it was everything. Now I'm going to show you how to use these files. So the first thing I have told you, you will need a beauty software. So I have downloaded all these files in a folder. So here is the application, beauty application. Open this application, and I am going to run a file which is already in the Nexus format. So I am not going to use CView. Here click on the file button, and here choose the import data. Here open the example file. In the data file you will get the apes.next, which is the exemplary Nexus file. Open this thing, and you will get here the partition name is as, file name is taxa. It contains 6 taxa, and there are 768 sites which is present aligned format. This data type is nucleotide. So here is a taxa, need not to test these things. Traits, sites. This sites window is important here. Here you can select the model which is juice canter, HKY, GTR, TN93. For using a substitution model, either you use the default settings which is given in the beauty, or you can also check which model you should use using the Mega software itself. So base frequencies is estimated. I am going to leave these things as it is. In clock section you will get the clock type. It is by default is given as strict clock, so need not to change these settings. In the tree file, tree prior, here you as we are making tree from the nucleotide sequences, and we are interested in speciation, so it is suggested that use the Yule process, which is there for speciation, and leave this setting as it is. Here in the state, also need not to touch these things. These are the priors. As we know, the Bayesian inference is based on the priors. So here also need not to change these settings. Operators is auto optimize. Bayesian inference will be auto optimized during its analysis. Here is the MCMC. This is the length of chain. How this is how long it is going to uh, make your run analysis up to 10 million. It is the echo state to screen every. It will sample your data after 100 chain is completed, and leave this setting as it is. Click here to generate a beast file. Now I'm going to save these things in the practice folder. Here you can say it is the suffix of this file is XML. So this is the file which we will be using. We are going to use 1 minute. We are going to use in our Beast software, Beast application. So now open your Beast application, and as I have told you, this contains thousands of trees. Actually, this Beast will run the Bayesian analysis. So here choose the XML file. Here it in the folder, it is the XML file type. It is written here, type XML document. So open this thing and leave all the setting as it is. Run this analysis. So here the summary of run, and it will take about 3 or 4 minutes to generate your dot trees file, which will contain the thousands of tree. And after that, when the our tree file will be generated, we will use our tree annotator to make your consensus tree with the posterior probability. Posterior probability, as I have said, it is the statistics of the reliability, as we see the bootstrap analysis when we run maximum likelihood. So it will take around 1 or 2 minutes. We will have to wait about that. The time it will take, it depends on your number of sequences. So as we have 6 taxa, a number of sequences, and also the length of the alignment, like it is the sequences which we are using is around 600 or 700 base pairs or nucleotide in length. So it is one of the software for Bayesian inference, Beast. You can also make your Bayesian inference Phylogram using Mr. Bayes, which I have found is very simple, cause this software, you can say here, you can see here that it uses around 5 or 6 application, but Mr. Bayes is simple. You will run only one application, Mr. Bayes, and it will generate all the files, and you can directly use that tree in your fig tree for drawing your phylogram. So it will generate a tree file, and the next application which we need is tree annotator. Here is the fourth one. Here you will have to specify the burn-in as the number of states. So as I have told you that what percentage of your run you want to burn in. Okay, so burning is burning is it will be the same number, the value you will put here, the same value you will be putting in the tracer, and in tracer, which summarizes the trees and help you choose to how many early low probability trees to discard. So here you will have to specify the burning. Here I am going to ten 1 lakh. Okay, 1 million. 1 million actually. Here you will input your tree file, which is going to generate from this run, and you will also have to choose the output file. Just choose a file and change the suffixes from that, so that you can identify your output file from that. Make it 10%, like we have here. You can read that 1 2 3 4 5 6 7 positions, and after we generally discard about 10%. 1 2 3 4 5 6 7. 1 2 3 4 5 6 7. So it is good. After it will reach to 100, then this is the value which is 10% of that. So we are waiting to generate our tree annotator to no, we are running beast actually to generate a tree file. So it takes around 7 minutes. You can see here the operation analysis. These are the priors which we have seen in beast or beauty. Okay, so now you can cancel that thing, and it is the window of tree annotator. Now we can choose the file. Here you can see the tree file, which is the result of beast, and now we are going to use this trees file in our tree annotator. So choose these trees file and choose an output file. Just use the tree, and here you can set that mc dot tree, because it is going to make an consensus tree. Total trees it will read is around 10,001, and it will be ignoring the first 10 million states, which will be around 1000 trees. Total number of clades, there are 8. And as I have told you, the function of tree annotator is to make a consensus tree, and it will also give the posterior probability on nodes itself. So the process is finished. Now you can cut that, and the next thing is you will have to run tracer. Tracer is in the another folder. Here is the tracer. Here tracer is nothing but, you can see here the summaries of those trees, and you can also decide the burning values here. Import trace file, and it is in the download section of beast. Remember the folder where you have saved these things, practice trees, and you will be using the log file for that. Okay, So tracer uses the log file. Here you can see that this is the trace, and here is the 10%, which is the burn-in state. There are 10 million states, and we have burn-in 1 million, so it is the 10% of everything, and these are the low probability trees, so this is discarded from the run. And here you can see the ESS value. So we are concerned for the ESS value. It is the effective sample size, and if the value of these is less than 100, so this is the bad sign, and if it is if the value is more than 200, so it is a good sign that your values are good. So you can say that it is in the thousand. So we can cut this thing. If you find that your ESS value is less than 100, so what you will do, you will have to increase this burn-in, and you will also mention in your paper or a research article somewhere that this is the number of burn-in. Okay, so everything is good. Now we have run the tracer, and now we have our consensus tree with the bootstrap value. We have checked the ESS value using tracer, and now you will be using the tree annotator file, which is inside the beast and tree annotator. Okay, we have already used, we have generated already. So tracer file is used to check the burn-in. If burn-in is incorrect or burn-in is low, you can make more trees to burn or discard it from the analysis. So actually I have done it before using tracer, but tracer should be used first, then your tree annotator, but everything is fine as we have seen in tracer. So now the generated tree file from tree annotator, we will be using our fig tree, which is the tree drawing program. Here is a fig tree application. Open that thing, and now you can see your generated tree file. Here file, okay, open, and here is the, you will have to tree file, not tree. Okay, trees file was used in tree annotator, and in this this is the output file of the tree annotator. So you will have to open the tree file, and here is the nice tree, but here you can see it is only the relationship is given, or the scale is given, but branch labels are not given, node labels. This is your posterior probability. You will have to posterior. This is the same as your bootstrap value for the nodes. So you can increase the font size, and tip labels you can also increase your names which is given. Okay, so this is this tree. You can modify this tree. You can also mention your paper what is the posterior probability of this node. It is the confidence that these clades are strongly supported in your analysis. You can modify these things, you can color everything, you can change font size, etc. So it is up to you how you are going to modify this tree, and in the end our goal is completed, and it is the Bayesian inference phylogram. Okay, so thank you for watching this presentation, and if you have any question you can ask to me now.